Hello everyone, this is Engineer Mohammad Samaslam. Today we are going to discuss about stiffness degradation. Actually, the researchers who deal with the cyclic loading, monotonic loading, or make the P delta curve or Skelton curve, they need to tell how the they need to tell the stiffness degradation. So what is it actually? It is the reduction in the stiffness or the rigidity of a material over a time under loading or under damage accumulation or under aging. So mostly it is observed in the concrete which experience degradation in stiffness under loading. So actually it is denoted by K. So what is K? It is stiffness coefficient, force over deflection, kilonewton per millimeter. So we actually in my paper I am following the two material, normal concrete and the ECC material. So I can calculate two stiffness coefficient K1 and K2 and then tell which material has low stiffness degradation and which is better. So this is actually this coefficient K specifies the how much the structure can resist under deformation. So the higher the value of the K, the stiffer the material will be. So how we get this graph? First of all, let me tell you this is for the ECC material, red color, and the black is for normal concrete. And you can see that the slope for normal concrete is much higher than the ECC. So the ECC stiffness degradation is much lower than the normal concrete. So it is better material. ECC is better material. And how we can get this graph? Let me tell you some concepts, and then I will share this file, my Excel loading protocol, and this graph origin file in the link. Then you can make changes in your according to you. So first of all, we need to know about this is actually the loading protocol, and we need to know at which drift ratio the specimen is failing. Actually, we are applying, this is a beam column joint, so we are applying load at the 1100 millimeter from the face of column. So for the normal concrete, the specimen is being destroyed at the 4.5% drift ratio. So it means that for normal concrete we will calculate the stiffness K value K1 up to 4.5 drift ratio, and for the ECC it is going up to 6% drift ratio. The failure is coming after 6%. So it means it is more ductile. So we will go up to 6%. We will calculate the value of K2 up to 6% drift ratio. And from the hysteresis curve you can also see that the slope for normal concrete, the reduction in strength is too much, so the slope is too much higher, see. And for ECC the slope is much lesser than normal concrete, so this has the low stiffness. And this is another paper where he calculated the stiffness, same, the load, peak load versus amplitude. So how we can get the value of K? I can show you my Excel file. First of all, let me tell you this is the data you get from the loading, and I have applied the load in the at the difference of 0.250, 0.25, 0.5, 0.751, and then I calculated the amplitude, the mean this is at distance, and then to make same unit I have applied by divided by 100. So I have this data, I have the data load deflection for normal concrete, load deflection for ECC. This is my monotonic loading or any P delta curve data or hysteresis curve data. So I told you that the normal concrete is being failed at 4.5% drift ratio or up to 50 millimeter, and ECC the maximum displacement we calculated is 66. So for normal concrete what we will do K1, and for ECC it is K2. So for normal concrete what we will do, I told you how we calculate the K value, load, deflection versus load, load versus deflection. Okay, load, this is load and this is deflection. So I need to start from the, see, I need to start from this value, 4 up to 4.5 or 5 maximum. So see what I have to do, 4.5, then 4, 3.5, 3, 2.52, 1.51, 0.5, 0.5. So it is maximum 12 values. Okay, so from here this is the maximum value. So what I have to do, I have to just highlight this, divide by, or I have to apply this formula, load versus deflection, and then a 4.5, like exactly you can choose any near value. So same formula, then I will again highlight this, and then 4%, this is 4%, and then this is 3.5%, 3%, and then 2%, and then 1.5, or like something near value. Any you can also choose this. I just choose for like smooth curve, and then 0.5, like 0, nearly 1, and then see, then it's same in the minus direction. This is how you calculate the K1. And for the ECC, I will go up from 6%. This is K2. Same load versus deflection. 6.5, 5.5, 5, 4.5, 3.4, 3.5, 2.52. Like it is like I have little bit difference, like, and then same in the negative direction. So I got the values for, like, then I will select all these values, like select all these values, okay, for K1, and I can copy this, and this is, see, you can arrange 0.5, see this one, 0.8, then 1.25, I copy like descending order from larger to shorter, okay. And here and also what I will do, yeah, this is, and then this is the deflection against it, 0.5, 49, 0.8, 44. So same process for the ECC. You will like arrange it from the descending order, larger to shorter, and then the deflection against it, see, 0.6 given. And when you get these values, then you can draw it in Excel, but I used actually the origin, and that gives better curve. So this is, then you put the values here, and it will give you curve like this. And you can also make some adjustment to like for smooth graph. And yeah, this is all I can show you. This is a graph, and I will upload this. I will upload this file, and you can then ask any question what you have.